Hello, welcome to the final episode of electromagnetism. It's the last dot point, and we're looking at Lenz's law and how it relates to the conservation of energy in two specific situations. Now, we've already looked at how it relates to DC motors. That's in back EMF. So we said that in a DC motor, the coils are moving in a magnetic field. This means they're experiencing a change in flux. Change in flux, according to Lenz's law, leads to an induced current. Now, if that induced current was in the same direction as the current from the battery, then that would increase the torque on the coil, and the coil would spin even faster. This would violate the law of conservation of energy, because then the faster the coil spins, the more change in flux, the more current, which means a faster spinning coil, etc., 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 infinite loop. We create so much energy that we get a black hole in that spot. No, that's not how it works. That's not how Lenz's law and conservation of energy work together. Instead, the induced currents are working against the current from the battery, reducing the amount of torque, limiting the speed of the coil. You don't get energy for free. Magnetic braking is similar. We have one type of energy turning into another, and we'll see that happen in magnetic braking. So there's a common situation you may have seen, whereas if you have a metal tube of some kind, and you drop a magnet through that tube, that the magnet will slow down. And I want to think about why that happens. So we have a magnet, and the magnet has its magnetic field, of course, down there and up here, boom, boom, boom. And the magnet is falling through the tube. So different parts of the tube are experiencing changing flux because the magnet is coming towards it or moving away from it. Okay, so let's say towards the bottom of this tube here, it's experiencing an increasing flux of these lines coming downwards. Okay, it's going to try and oppose that change in flux. That's what Lenz's law says. It's going to oppose it by creating an upwards magnetic flux of its own. Okay, how does it create that flux? We use the right-hand grip rule. Thumb points in the direction of the flux being created. Your fingers are in the direction of the currents, the eddy currents. So eddy currents going around, if I'm looking from the bottom, they would be clockwise. Yep. So looking from the bottom, currents are actually coming across the front like this, and then around the back like that, in order to create these upwards magnetic field lines. Okay, this is essentially like a North Pole here facing the North Pole there. What kind of force does that put in? It repels it. So this north repels this one, which slows down the fall. Okay, so we get a force upwards on the magnet, slowing it down. If we look at the top, what happens up here? So again, let's do it in blue. The top of this metal cylinder is experiencing a decreasing magnetic field. It's got these field lines going through it, but they're moving away as the magnet falls down. So it wants to increase it again by creating its own flux in this direction, right? The field's decreasing, so it wants to bring it back, oppose that change. How do we do that? Right-hand grip rule, thumb points down because that's the direction of magnetic field now, and I can see that my current is in the same direction as the current that we had below. It's going across and around the top like this. Okay, this is essentially making a north pole on this side, which pulls the south up. Okay, pulls the south up again, causing that magnet to slow down in its fall. And that's what you see. You get a strong magnet, not just some bar magnet. You get a strong magnet. You drop it through an aluminium or copper tube. That magnet is going to slow down as it falls. Okay, this is magnetic braking. It's braking because it's slowing down. How does it relate to conservation of energy? Well, we're losing one type of energy, aren't we? We're losing the kinetic energy of the magnet. Is that energy just disappearing? No, it's changing into different types. It's changing into electrical energy in these currents, and those currents will heat up the sides of the coil. So that's the sides of the tube. So it's turning into heat. We're converting motion to heat. It's very similar to friction, except no surfaces need to touch at all. This applies whenever any magnet moves past a piece of metal, or vice versa. The metal can move past a magnet. So this is commonly used in roller coasters to slow them down. Okay, in a roller coaster, you will have you have the car that the people sit in. There we go, they're having fun. And the car's got wheels. And at the bottom of the car, there'll be a sheet of metal, right? A sheet of metal. And on the tracks it's about to go to, there will be some strong electromagnets at the end where it needs to brake, okay? These are electromagnets, and inside the electromagnets there's a magnetic field. Let's say it's going into the page, boom, like this. And so when the cart goes over that, these magnets will be behind the metal sheet, and there'll be some magnets in front of it as well. Let's say these ones. Um, yeah, let's say these have X's as well. Let's say these magnetic fields go across like that, and this metal sheet runs in between them. Okay, goes in between them like that. Now, the front of the metal here, when it experiences an increasing um, magnetic field in that direction, it's going to oppose that change, creating its own magnetic field in the other direction. That's going to repel it from this, pushing it backwards. However, once it's inside this magnetic field and is moving past it, it's going to have a decreasing magnetic field. Generally, when it's going towards the the electromagnets push them back. When it's trying to go past them, the electromagnets are going to pull them back. They're going to push them away if they're coming towards it, or pull them back if they're going away from them. Either way, it's braking. And this conversion of energy, kinetic energy from the roller coaster, is just going to heat up this metal plate down the bottom here, heat it up quite a lot. Okay, you'll find this in more rides, so the ones that lift you up, and then drop you. And when it falls, there's actually a very smooth stop right at the end. The reason why it's so smooth is the amount of braking depends on the speed of the object. So the faster speed, that's a faster change in flux, which means you get a bigger braking effect because you get more induced current. Slower speeds, you get smaller flux. So as it slows down, the flux decreases proportionally and you get a really smooth, slow braking effect. You can see videos online where people get a giant slab of aluminium or copper and they drop a rare earth magnet onto it and it falls very satisfyingly slow on top of it. Or vice versa, you can have a very big magnet and you can lean up a slab of aluminium and then tip it over and it will fall and it will hit very slow and satisfyingly. That is the last bit of electromagnetism. We're on to the nature of light next.